everyone. In this video, we are going to rank resonance structures. So in previous examples, we've seen resonance structures that have the same energy, or also called degenerate. But some resonance structures can contribute more than others depending on the molecule. So for instance, let's say you have carbon monoxide. And this is the Lewis structure for carbon monoxide. Now, you could move one of these pi bond electrons over to oxygen since it is more electronegative. And then that would give us the following molecule. Okay, so oxygen is happy there, but carbon isn't. Carbon doesn't have an octet. So that leads us to our first rule. Full octets take priority. So that first Lewis structure is the major contributor to the hybrid structure, and the other Lewis structure is the minor contributor because it does not have a full octet, at least for carbon. Number two, if octets are met for all of the atoms, then the structure with minimized charges is the major structure. So we want molecules, or our structures for the molecules, to be neutral. So if you do have a resonance structure that leads to charged atoms, then that would probably be the minor structure. Number three, if conditions 1 and 2 are met, then look at electronegativity of atoms. So negative charges should be on electronegative atoms, and positive charges should be on less electronegative atoms. So if you do have a molecule with charges and you can't avoid having charges, then again, the negative charges should be on more electronegative atoms. And then the last rule, we want to avoid structures with negatively charged carbons and positively charged carbons next to each other. So as an example, let's say we have this molecule with a double bond between the carbons. Now we could move that pi bond over, or the pi electrons over, and that would give us this structure where one of the carbons has a lone pair of electrons and is negatively charged, and the other carbon has a positive charge. But we don't want that because carbons prefer to be neutral. So that would be a very minor contributor to the hybrid structure. And this structure on the left would be the major contributor to our structure. All right, so let's go over a practice problem. Oh, let's see, let me find my notes. They're all over the place. Okay, so let's look at this molecule where a carbon has a double bond to oxygen, and then it's bonded to a methyl group, CH3, and then it's bonded to CH2, where the carbon has a lone pair and a negative charge. Okay, so let's figure out some of the resonance structures here. What could we move around? So let's move the pi electrons up. So just go with me on this one. This is kind of going against what I've told you earlier, so if you're confused, that's okay. This is kind of just for the sake of the example. All right, so when we moved that the pi electrons up onto oxygen, that oxygen became negatively charged. And actually, let me redraw that because it looks kind of like a positive charge. There we go. So carbon in the middle has only 3 bonds. So that means it is positively charged. It's missing some electrons. Okay, so one way we can fix that is by moving the lone pair of electrons on carbon over so that now we have a double bond between those carbons. Okay, so these are our resonance structures. And now let's rank them. So which resonance structure is our major contributor? Which one follows all of the rules? Okay, so let's think about octets. Which structures have octets for each atom? So this one does, this one does. Okay. Now rule number 2. If tied, the structure with the minimum charges is the major structure. Well, both of these structures have a negative charge. Okay, so they're kind of still the same. So let's go to rule number 3. If still tied, then let's look at the electronegativity of the atoms with the negative charge. So we want the negative charge to be on the more electronegative atom. So in the structure on the left, the negative charge is on the carbon. In the structure on the right, the negative charge is on the oxygen. And which one is more electronegative, carbon or oxygen? Oxygen, right? So we want the negative charge to be on oxygen. Okay. So that means the structure on the right is the major contributor. Okay. Let me just get rid of these check marks here. So this is the structure that will contribute the most to our hybrid structure. All right, so then now we have to decide between the other 2 structures, which one will contribute more than the other. Now, neither of those 2 structures are great. We already said that carbon would rather be neutral than have a negative charge. But if we look at those 2, this structure in the middle has a positive carbon and a negative carbon right next to each other. So that one is the worst contributor, right? So this would be very, very minor in terms of how it contributes to our hybrid structure. And then the structure on the left will be a minor contributor. It's not as great of a structure compared to our major contributor, but it's still a somewhat valid structure. It does fulfill the octet rule, and it does have minimum charges. Okay, so let's draw the hybrid structure. Okay, so those pi electrons are delocalized across the oxygen and those two carbons on the left or the right-hand side. We have some lone pairs on the oxygen, and that oxygen is partially negative, and the carbon is partially negative. The carbon and the oxygen do share that negative charge, but the oxygen is more likely to be negatively charged. Okay, so the structure in the middle, the resonance structure in the middle with the two charged carbons, because it is very, very minor, we typically don't include it when we're drawing resonance structures. So let me just make a note here. So typically we don't show very minor contributors. Because again, if they're not really contributing to the overall structure of the molecule or the hybrid structure, then, why even draw it? So what we would typically show instead is that lone pair on carbon moving over, and then the pi electrons on oxygen moving up. So we would show that all in one step. Okay, so let's look at some resonance patterns. Oh, sorry. So number one, we have lone pair sigma pi. So if you have a structure like this one, where you have a lone pair, a sigma bond, and a pi bond all right next to each other, then that means that you probably have a resonance structure. Number two, if you have a cation next to a sigma bond next to a pi bond, so similar to our allele cation, then you also can have a resonance structure. So let's actually look at another example of that too. Let's say you have a six-membered ring, and remember each those vertices represent carbons. And let's say we have a bond to oxygen on the top. And let's say the carbon below it is positively charged. And then let's also say we have a pi bond. So this shows that we have a cation next to a sigma bond next to a pi bond. So this is also a situation where we could move some electrons around and find a resonance structure. Now there's a couple more. Number three, if you have a non-carbon-carbon pi bond. So let's go back to that first structure, except let's say that all the carbons are neutral. We do have a double bond between oxygen and carbon, and oxygen is electronegative, so it does like electrons. So you could move those pi electrons up to create a resonance structure. Now, it might be a minor contributor to the overall hybrid structure, but it's still a valid resonance structure. And then number 4, aromatic ring systems. So this is something we're going to talk about in the future, but an aromatic ring system is something like a benzene ring, where you have 6 carbons all connected in a hexagon, and then we have alternating pi bonds. So what's really cool is that those pi electrons are delocalized all the way around the ring. So we could move these around and still have a valid resonance structure. And this actually gives us a hybrid where those pi electrons are just delocalized all over that ring. And sometimes people will draw this as a hexagon with a circle in the middle, just to indicate that the pi electrons are everywhere, basically. All right, so these are the patterns to look for. So again, number 1, a lone pair of electrons next to a sigma bond next to a pi bond. Number 2, a cation, so a positive charge, next to a sigma bond next to a pi bond. Number 3, a double bond between 2 atoms that are not carbon, or maybe one is carbon and the other one is electronegative. And then number 4, an aromatic ring system, like benzene. And again, we'll talk more about aromatic systems later. All right, so if you want more practice with these resonance patterns, I recommend trying the Skill Builder exercises 2.8 and 2.9 on pages 77 and 80. And I do recommend that you do those Skill Builder exercises. It will give you so much more practice with the material, and you'll be much more prepared for exams and quizzes. Okay, so that is the end of chapter 2. It wasn't quite as long as chapter 1. So the next video we'll start getting into chapter 3. So I will see you then.